Okay, let's find the Taylor series for 1 over the square root of x centered at c equals 1. Okay, so Taylor series for 1 over root x centered at c equals 1. We're going to get started. So f of x, I'm going to write it as x to the negative 1/2. Actually, let's do it in green. F of x is equal to x to the negative 1/2. So f of 1 is just equal to 1 to the negative 1/2, but still just 1. So then f prime of x is equal to negative 1/2 times x to the negative 3 over 2. So f prime of 1 is equal to negative 1/2 times 1 to the negative 1/2, which is just to the negative 3 over 2, which is just 1. Now then f double prime of x is equal to negative 1 over 2 times negative 3 over 2 times x to the negative 5 over 2. Now remember what we said about negatives. If it's negative, just leave one negative and move it to the front. If it's positive, we can get rid of all of the other negative stuff. So I'm going to say f double prime of 1 is going to be positive, so I'm just going to get rid of those negatives, and I'm going to write the 1 and the 3 on the top, and the 2 times 2 on the bottom. Now, what's next? F triple prime of x will be 1 over 2 times 3 over 2. Notice I didn't write those negatives. I don't need them. That was positive. But I am going to write the negative for the negative 5 over 2 that I bring down. So times negative 5 over 2 times x to the negative 7 over 2. This is negative. So we said triple prime of 1, bring the negative to the front, negative 1 times 3 times 5, all divided by 2 times 2 times 2. Okay, let's just do one more. I think we see what's going on. That x, when we're going to plug in 1, it's just not going to be there. But each time I'm multiplying that new power down. So my fourth derivative here at x is equal to, we had that negative, so I'm going to leave it 1 over 2, 3 over 2, negative 5 over 2, negative 7 over 2, x to the negative 9 over 2. And the fourth derivative evaluated at 1 will be negative. So I keep one negative. I'm sorry, it will be positive. What am I saying? It will be positive, so I just get rid of the negatives. And I have 1 times 3 times 5 times 7 over 2 times 2 times 2 times 2. Okay, so the bottom, the denominator here is actually pretty easy to understand. So I can see that this is going to be something over 2 to the 4th. This will be something over 2 cubed. Something over 2 squared. Something over 2. And then to the 1. And then 2 to the 0 is just 0, so that could be over 2 to the 0. We can count that. Now we also can see that this is alternating. First I have a negative here. Then I have a positive. So here we're going to have, let's just write down our n values. This is n is equal to 0. N is equal to 1. N is equal to 2. N is equal to 3. N is equal to 4. So when n is 4, I want a positive value. But when n is 3, I want a negative value. So I'm going to have that negative 1 to the power of n. I don't need an n plus 1 because I need to plug in an odd number and have it be negative. So when I'm thinking about what my a sub n is going to be, that a sub n is going to contain that negative 1 to the n, and it's going to have the 2 to the n on the bottom. So then the question becomes, what's going on the top there? So I have 1, and then I have 1 times 3, and then I have 1 times 3 times 5, and then 1 times 3 times 5 times 7. So this is not a factorial because it's not containing all of the numbers below 7. It's only containing the odd numbers below 7. If we look at what's going to happen if I take the fifth derivative, then I'm going to be multiplying that negative 9 over 2 down, and I'll go on to the 9. So the question is, how do I represent this? Well, we saw things like this when we were doing the ratio test, and we saw that really we just kind of have to like write them out big. And that's what we're going to do. But to figure out how I'm going to write this out big, so the numerator is going to be 1 times 3 times 5 times 7 dot 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 times something. So the question is, what goes there? The thing that I really need to be looking at here is the last number that shows up in this sequence of numbers. So I have like 1, 3, 5, 7, right? So we can see that that is 2n minus 1. But if you can't see that, that's okay. The sequence that we have here is an arithmetic sequence. And notice I'm just starting at 1 because typically we start sequences when n is equal to 1. So my first term here, my a for this arithmetic sequence is 1, and my d is 2. So I can plug this into my formula for an arithmetic sequence, 1 plus n minus 1 times d, and get that this is 1 plus 2n minus 2, which gives me the 2n minus 1 that goes right there. So that thing right there, there's a whole thing right there. All of that expansion is my numerator. I just realized I need to put the 1 over n factorial over here for my a sub n. So then my fn, my nth derivative evaluated at 1 is going to be 1 times 3 times 5 times 7 dot 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 times 2n minus 1, all divided by 2 to the power of n. And then we also are going to have the negative 1 to the power of n out front. Now, the question is, did I skip anything? Is there anything that does not fit this pattern? So we started that sequence there at n equals 1. But the question is, does f of 1 fit the pattern? So why don't we start out by writing actually our a sub n, the a sub n that we got by figuring out the pattern for the nth derivative, and see if when I plug in 1, I get 1. So my a sub n then will be equal to negative 1 to the n, 1, 3, 5, dot, 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 2n minus 1, all over 2 to the n. So a sub 1 based on this would be negative 1 to the 1, so that's negative 1. And well, then if I plug in, I'm sorry, we're plugging in 0 here. What am I doing? A sub 0 would be, well, what does that even mean here? If I do 1, 3, 5, 7, 2 times 0 minus 1, that doesn't really even make sense. I kind of get a negative 1. So then I would have like negative 1 over 2 to the 0 times that negative 1 to the 0, and that would result in a negative 1, not a positive 1. So a sub 0, we can say that it's a little bit unclear what it even is based on the way that we've defined that numerator. So we're just going to say, it kind of seems like it would be negative 1 / unclear. We're going to leave it out of the pattern. So what that means is, what we were looking at is 1 over the square root of x. My 1 over the square root of x is going to be 1 plus the sum n equals 1 to infinity of negative 1 to the n times 1 times 3 times 5 dot 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 2n minus 1 all over 2 to the n. I need my n factorial that I once again forgot to write up here, n factorial, then times x minus 1 to the power of n, and that is my final answer. Okay, so in this one, we had that kind of weird thing happening in the numerator where we were like skipping numbers for our factorial. Now let's see what happens when every other derivative is 0. And that's going to happen when we have trig functions like sine or cosine x. So let's find the Maclaurin series for f of x equals sine x by writing the degree 7 Taylor polynomial. That means I got to take 7 derivatives. So remember, Maclaurin series means that my center is equal to 0. So f of x is equal to sine x. F of 0 is sine 0, which is just 0. F prime of x is equal to cosine x. f prime of 0 is just 1. Now f double prime of x is going to be the negative sine x. So at f double prime of 0, I'll be at negative 1. And I'm going to have to keep doing this all the way up to 7 because I want my degree 7 Taylor polynomial, and that way we're really going to be sure that we got this down. So triple prime of x will now be negative cosine x. So wow, that's a 0. I can do math. Sine of 0 is 0. F triple prime of 0 is negative 1. Then the fourth derivative will be the derivative of negative cosine. So that brings us back to the positive sign. We're actually starting over. So my fourth derivative will be 0. My fifth derivative, we're back to cosine. So my fifth derivative, we're back to 1. Then my sixth derivative, we kind of know what's going to be happening here. We can really see the pattern, but we're just going to keep going to get to that 7. My sixth derivative will be a negative sine x. So my sixth derivative is at 0 is back to being 0. And then my last one that we need to do here, negative cosine x, that's going to give me a negative 1. Okay, so let's actually write our 7th degree Taylor polynomial. So I'm going to have t sub 4, by 4 I mean 7, t sub 7 of x. Well, my first thing that I had there was a 0. So this is going to be 0 over 0 factorial. Well, that's just 0. Plus, then I have a 1 over 1 factorial times x, because our center was 0, plus 0 over 2 factorial times x squared, plus negative 1 over 3 factorial times x cubed, plus 0 over 4 factorial x to the 4th, plus 1 over 5 factorial x to the 5th, plus 0 over 6 factorial x to the 6th, and then minus, or rather plus negative 1 over 7 factorial x to the 7th. What we notice here is that all of those things that gave me a 0 just don't show up. So my actual 7th degree Taylor polynomial here is actually just 1 over 1 factorial x minus 1 over 3 factorial x cubed plus 1 over 5 factorial x to the 5th minus 1 over 7 factorial x to the 7th. Now, the question is, how do we deal with it? So every other term we see is going to be 0. What that means is when I'm trying to find a pattern, I need to not have an x. I need to not have an x. I mean, not have that first 0. I need to not have an x squared. I need to not have an x to the 4th and an x to the 6th. In other words, when I plug in values, I'm not going to have every other one spit out a 0. I'm just going to have it only spit out the things that I have here. So what that means is I'm not going to have an in value that gives me that first 0. This is going to be n equals 0. This will be n equals 1. This will be n equals 2. This will be n equals 3. So in other words, n equals 0 is not going to spit out a 0. It's going to spit out 1 over 1 factorial. N equals 1, well, that's going to be that negative 1 over 3 factorial x cubed. I'm not going to be spitting out that second 0 there, if that makes sense. So we need to find our pattern based on what's going on right here. So what I can see in the denominator is my factorials in denominator. When I have 0, I have a 1. When I have 1, I have a 3. When I have 2, I have a 5. When I have 3, I have a 7. So to get from one factorial to the next, I'm always just increasing by 2. So my first value, my value when n equals 1, is 3. And my common difference here is 2. I actually have an arithmetic sequence in the factorials. So I will have 3 plus n minus 1 times 2, which gives me 2n plus 1. Now, maybe you could see that without actually plugging into the formula for an arithmetic sequence. When you plug in 1, you want 3, so that's just 2 times 1 plus 1. When you plug in 2, you want 5, so that's just 2 times 2 plus 1. So maybe you can see that, and that's totally fine. Notice, and so you don't actually have to plug into that formula. Now, I want you to notice that the factorials that I have down at the bottom, that 3 factorial is the same as the power of x. So the powers of x are the same as my factorials. Okay, so that means that my a sub n, well, first of all, it's alternating. When I plug in 1, I want it to be negative. When I plug in 3, I want it to be negative. So plugging in odd values makes a negative. So we saw that that's negative 1 to the n. Then I have a 1 on top. But instead of having n factorial on the bottom, I have 2n plus 1 factorial. That's my a sub n. Then when I go to my actual power series, my sine x will equal to the sum n equals 0 to infinity of negative 1 to the n over 2n plus 1 factorial. But remember, I don't need this to be spitting out an x or an x cubed or an x squared. Wow, I can't talk. I don't need this to be spitting out an x squared or an x to the 4th or an x to the 6th. So we're using our same power for the factorials up here. So I end up with negative 1 to the n over 2n plus 1 factorial times x to the 2n plus 1. The power of x ended up changing as well. And that is the Maclaurin series for sine x. Hopefully you were able to follow that. It does get a little bit confusing with these trig functions sometimes. That's all for now. So in the next time, we're going to see how we can use series we know. So like by knowing the series sine x that we just derived, we can use that to find other series where it might be more complicated to find a pattern in the derivatives. That's all for now. Bye, guys.